Let's take a look at this next example, example number 13. For this one, it's a graphing problem. They're asking us to graph one complete cycle of y equals 1 minus 8 sine squared of x over 2 times cosine squared of x over 2. Now, in what we've learned about graphing, we never learned how to graph the product of two trigonometric functions, or even worse, anything that involves a square of a trig function. Right, so we're going to want to use the identities to simplify this into something that we do know how to graph. Okay. And this one is a little bit tricky. It's not by all means obvious what we should apply, especially because the angle is not even by itself, right? It's not just like x, there's an x over 2. So my suggestion is whenever that happens, replace the x over 2 with a single variable. That way it's easier for us to focus on the bigger picture and what is the overall form of the expression and what might fit, which identity might fit into the expression that we have. Okay, so for now, I'm just going to let A represent x over 2. Okay. And when we do that, we're going to get y is equal to 1 minus 8 sine squared of A times cosine squared of A. All right, so now that we have that, here's one thing that we can try. And again, it's not obvious. I'm giving you this tip because I've tried several problems, and as you guys grow in your math, experience, you're also going to attempt several problems, and eventually you're going to start having a good feeling about what might work and what might not work. And so, based from the problems that I've tried, whenever you have sine, it's just like a sine squared times a cosine squared, or even just a sine times a cosine, something that is pretty helpful is the double angle formula for sine. So let me show you what that looks like. Okay, it looks like sine of 2 theta is equal to 2 times sine of theta cosine theta. Okay, so what I'm going to try to do here is manipulate this a little bit so that I can replace 2 sine theta cosine theta with a sine squared of 2 theta. Okay, so let's try that out. I'm going to write this as y equals 1 minus a 2 times 2 squared, right? Because 8, I can split it up into a 2 times 4, times sine squared of a cosine squared of a. And then all of these factors have a square. So using our power rule, I'm going to pull that out so that we have 2 sine a cosine a, everything squared. From this step to this step, I'm using power rule for products. Okay. And now this is nice because the 2 sine a cosine a, we can apply the double angle formula and get sine of 2a. This is 1 minus 2 sine of 2a, and that's squared. Okay, so this is by double angle formula. And it's replacing this part with this. Okay. And then again, because we have an angle that has attached some constant, and I just want to focus on the bigger picture, not so much, not have to worry on what's this angle. Let's just replace that with theta. Okay, so I'm going to let theta be equal to 2a. And so this is 1 minus 2 sine of theta squared. So this can just be written as 1 minus 2 sine squared theta. Now let's go back to identity sheet. Is there anything that looks like 1 minus 2 sine squared theta?
The double angle formula. Remember the third one?
Yeah, very
cosine?
good. So double angle formula for cosine, the version number 3, it says cosine of 2 theta is equal to 1 minus 2 sine squared theta. So that's what we're going to apply here. This is cosine of 2 theta, and that's by double angle formula. Cosine version 3. Okay, so that's way simpler than what we had originally. It's a lot nicer. Okay. The only thing is we're not completely done yet because the original variable we had was x. Here we've turned it into theta. So now we're going to have to go back and replace the original or replace the variables until we reach the original x variable. Okay, so first taking the theta and replacing it back in, we're going to get cosine of 2 times 2a here, and just taking this theta equals 2a and replacing it there. And so that gives us a cosine of 4a. Then I'm going to go back to what was a. A was this x over 2. So I'm going to replace it into here. We're going to get cosine of 4 times x over 2. Okay, this is the a part. So then the 4 and the 2 are going to cancel to give us just the 2. So this is cosine of 2x. So the final equation that we're working with, or that we're trying to graph, is y equals cosine of 2x. Questions there? You guys want to take a moment to digest the math? So now that we have it in a form that we know how to graph, let's go through the steps for graphing. The first step is to find what the period it will be. And remember, the period is always 2 pi divided by b. In this case, b is 2. Remember, b is always the coefficient of the variable. So we're going to get a period of pi. Then the next step is to find the step size. And that's going to be the period divided by 4. So that's going to be a pi over 4. Then the next step is to find the important x values. And here we don't have a horizontal shift to worry about. So we can use directly the step size to just find those x values. And we'll do so by saying x0 will be 0 times the step size. So that'll give us 0. Then 1 times the step size. So that's a pi over 4. 2 times the step size. So that is a pi over 2. 3 times the step size. So we get 3 pi over 4. And finally 4 times the step size, which is going to be a pi. Now we take those x values, replace them back into the equation, and get out the corresponding y values. Okay, so just make sure that we're working in radian mode now because these x values are in radians. So if you haven't done so already, you can go ahead and change it. Then we have y equals cosine of 2x. So we're going to have cosine of 2 times 0. That's the first x value. So that gives us a 1. Means that first y value is 1. Then we're going to replace in a pi over 4. So we'll have pi over 4. And that gives us a 0. Then the next x value is a pi over 2. So that gives us negative 1. Then it's a 3 pi over 4. And that, okay, so this, whenever we have this, remember we said sometimes a calculator has round off errors. So if you ever see one time, this is times 10 to the minus 13, they just write it more compactly in this form. But you can interpret that to mean 0. It's just a round off error from the calculator, but it's actually just 0. And then the final one is pi that we have to substitute in. So I'm just going to erase everything but pi. And we get 1. So we're going to have a pi over 4, pi over 2, 3 pi over 4, and pi label. Then we also need to have a 1, a negative 1 in the y direction. So we start off at 0, 1. Then we go to pi over 4, 0. Pi over 2, negative 1. 3 pi over 4, 0. And pi, 1. I guess it's, let me just highlight these so it's easier to see which numbers we're graphing. We're plotting. Goes there. Alright, so that means that our graph, oops, looks like the usual cosine graph. The main difference being that we complete one cycle in pi radians rather than 2 pi radians. And that makes sense because if we look at the formula, nothing has changed other than the period because of this b. Okay, but there is no change in the amplitude, there is no vertical shift, there is no horizontal shift, just the period. Okay, any questions there? We have one more problem that is very similar to what we have there. We have to graph 4 tan x times cosine squared x minus 2 tan x over 1 minus tangent squared x plus 1. Again, this is extremely ugly. We've never had to graph anything like that in the past. So we're going to try to use our identities to boil it down to something that is simpler and of the form that we know how to graph. So with this problem, I would encourage you to focus on either numerator or denominator first and try to see what can be done to that. So if I look at the numerator, for example, the one thing that catches my eye is the fact that I have a 2 tan x in the second term, and you can also see a 2 tan x in the first term, right? It's just this 4 that's there. But I could factor out a 2. And so the reason why it draws my attention is because I can pull out, that means I can factor out a 2 tan x from the numerator. So that's what I'll do and see if it leads me anywhere productive. If it doesn't, that's okay. Sometimes it's a trial and error type of process. Okay, so if I pull out a 2 tan x, here this 4 is going to become a 2. The tan is going to cancel out because remember, when you factor, it's like you're dividing by whatever you're factoring, right? So It's like dividing by this 2 tan x. Okay, so this 4 becomes a 2. The tan x cancels out, and we're left with the cosine squared x minus 2's cancel and tan x cancels, leaving us with just a 1. So that's in the numerator. The denominator, we haven't done anything to it, so we're just going to write it the same. 1 minus tan squared x. And then we have this plus 1 that we need to bring down, this plus 1 constant. Okay. Now, again, it still looks quite a bit complicated. I have tan x's, but tan x being multiplied with the 2 cosine squared minus 1. So because there are no formulas or identities that have that type of product, a tangent with the 2 cosine squared x, I want to separate all of the tangents from the cosines. So what I mean by that is similar to what we did at an earlier problem. I'm going to break this up into the product of 2 fractions. The first one will have 2 tan x over 1 minus tan squared x. The second one is going to have the 2 cosine squared x minus 1 over 1. And then we still have to bring down this plus 1 constant. And so that brings down. But these, I separated them into 2 fractions. One that has these, this tangents, and another one that just has the cosine. Okay. You would always verify if you've separated this correctly by multiplying back and seeing if you have this original statement. 2 tan x times this 2 cosine squared minus 1 would give us the numerator, and 1 minus tangent squared x times 1 would give us the denominator. Okay, so nothing has been done to change it. We've just separated into 2 fractions. Okay, this is good now. And the reason why I'm saying that is because 2 tan x over 1 minus tangent squared x actually boils down to something much simpler. Take a look at the identities. So we see what can be applied just for this part here.
It's a double angle formula.
Yeah, very good. It's a double angle formula. Take a look at this last one here. 2 tan theta over 1 minus tangent squared theta is tangent of 2 theta. That's what we're going to apply here. We're going to get that this is tangent of 2x. And then I'll write the reason here. This is by double angle formula. And then we still need to bring down the times to, and I'll write actually parentheses around this because there's two terms in the second factor. So it's 2 cosine squared x minus 1. I won't write over 1 anymore because we no longer have a fraction in the first term, or the first factor, I should say. So I'll just write it like this, and then we have the plus 1 that we need to bring down. What about this second one? Is there anything that we can apply for 2 cosine squared x minus 1?
That's also a double angle formula. It's the second version of the cosine 2x.
Very good. Yeah, that's also double angle formula. So let's apply it, and we're going to get tangent 2x times cosine 2x plus 1. Very good. Okay, so it's a lot simpler than how we started, but it's still not simple to the point that we know how to graph. So let's see what else we can work here. Whenever you have tangent times cosine, or even tangent times sine even, try to write the tangent in terms of the identity, the sine over cosine identity. Okay. And so this formula, if we were to replace theta with 2x, This would be saying that tangent of 2x is equal to sine of 2x over cosine of 2x. So that's what we're going to use here. We're going to say this is the same as sine of 2x over cosine of 2x. And then we have times cosine of 2x, and here I'll write it over 1 because we have a fraction in the first factor, plus 1. This is by tangent infinity. And I forgot to write the reason for the previous step, but we'll do that. We'll write that in right now. Okay, so this step, that was by double angle formula for cosine, version 2. All right. So notice what happens now. Now we have cosine 2x in the numerator canceling with cosine 2x in the denominator. And the only thing that we are left with is y equals sine 2x over 1, which is the same thing as sine of 2x, and then plus 1. And that is simple enough that we know how to graph. All right, so let's go through the steps just like what we did earlier. Step 1 is to find the period, and it'll be 2 pi divided by b. In this case, we have 2, so we're going to have pi for period. The next step is to look for the step size, and the step size will be the period divided by 4, so that's going to be a pi over 4. And so just like in the previous problem, we're going to get the same x values by multiplying the step size with 0, 1 through 4. So we're going to have x0 is 0, x1 is pi over 4, x2 is pi over 2, x3 is 3 pi over 4, and x4 is pi. Again, I'm skipping, oh sorry, no, push this up. I'm skipping the work, or just the 0 times 1 times 2 times, because it's exactly the same thing that we got for the previous problem. Okay, and then we plug it into the equation. Notice because we have this plus 1 constant, that means that we should see the sine graph shifted up by 1, and the period would be just pi instead of 2 pi. Okay, but let's go ahead and punch that in. So I'm going to have sine of 2 times x, so here it's going to be 2 times 0, and then we have plus 1. Make sure that you close the sign. Okay, so if you're using parentheses inside for the product, that's okay, but make sure that you have that extra parenthesis to close the sign, and then put plus 1. So the first y value is 1. The next one we're going to replace 0 with the pi over 4. So this is pi over 4, and we get 2. And then we replace with pi over 2, and that's 1. Then we replace with 3 pi over 4, and that's 0. And finally we replace with pi, and that's a 1. All right. So we'll draw the tick marks: pi over 4, pi over 2, 3 pi over 4, and 5. Then in the y direction, we need to label the 1 and the 2. And that's the highest is the 2, lowest is the 0. So we should see the graph oscillating here. And we start at 0, comma 1. Then at pi over 4, comma 2. Then at, oh, sorry, what did I write? Pi over 4 comma 2 is up here, not down here. Okay. Then pi over 2 comma 1, 3 pi over 4 comma 0, and pi comma 1. So we see the sign graph oscillate like this. And that makes sense because normally sine begins at 0, 0, but because we have this +1, it's like this x-axis has shifted up to this part here, right? So that now it's oscillating about y equals 1. Okay, this is y equals 1. And we still have the amplitude of 1. We have a period of pi, which makes sense because of that too. And there's no reflection because there is no negative in front of the sign. This looks good.